Alright, welcome back to Inorganic Tutors Institute. In today's lecture, we are basically going to deal with some few problems in introductory analysis. You know what? We will come back to structure the course on the channel for your understanding. This is just the preliminaries to the course. You know, introductory analysis can be a bit confusing if you don't get the right tutor or the right person to take you through. So that is why Inorganic Tutors Institute is right here with you to handle everything perfectly for your understanding. Right, so this is just the preliminaries, okay? And so we are going to solve about 4 problems, and we will end there we will come back to structure the course on the channel. All right, so the first problem is, we call it question 1a, right? We want to prove that the limit as n approaches infinity of 2n plus 5 divided by n plus 5 equals what? 2. So what we want to do is to prove that this particular limit is equal to what? 2. This particular function, the limit is what? 2. So we have done a whole lot of limits, so many limits in what? Calculus, right? But in here, we are going to apply some slight changes, but it's almost the same, right? They are all the same, all right? So what we are going to do is first, we're going to use the epsilon, right? But this time it's not going to be epsilon delta, it's going to be epsilon to a certain number, right? So let's say that this is the problem. 2n plus 5 divided by n plus 5 equals 2, right? This is the problem that we have at hand. So how do we handle this? Very easily. First of all, let's a subscript n be equal to the whole function that we were given. This is the function 2n plus 5 divided by n plus what? 5. Okay, now we wish to prove that this particular limit is equal to what? 2. All right, so now that we have let this equals that, then let's rewrite the function. So now this is what? An equals 2. So we want to prove, or we wish to prove, that this thing is equal to what? 2. All right, so this is where we are going to use the epsilon to a particular number proof, right? So epsilon to a number proof. Epsilon to a number proof, right? So first of all, let's, as usual, epsilon must be positive, right? If epsilon is positive, right, epsilon must be positive, right? Then we must find a particular number, all right, that belongs to the set of natural numbers. Okay, this is a particular number that belongs to what? A set of natural numbers. So that is what we are going to do. Okay, so such that for n greater or equal to that particular natural number, all right, such that for a small number should be greater or equal to the number that we are looking for from the natural numbers, right? So this is n. All right, so once we have been able to do this definition, then the next thing we have to do is, that absolute an minus what? 2, or let's call it limit first, absolute an minus, or let's go back from the basics, okay? From the basics. You know that the function minus the limit must be less than epsilon. This is what we know from calculus, right? So here, the f of x is this, of which it was this, of which we represented it to be what? An. So we have an minus the limit was given as 2. So we have 2 here, and that should be less than what? Epsilon. Okay. Once we have been able to do or define this, the rest is algebraic manipulations, as we know. All right. So now, absolute an minus 2 is equal to, we are going to substitute the function inside, right? So this here is 2n plus 5 divided by n plus 5 minus 2, the limit, right? So minus 2 here. Okay, so this is what we have, all right? So we are going to simplify this. So we find the LCM, then simplify, all right? So here, we're going to have 2n plus 5 minus 2 into, you know, this is over 1. So the LCM here is n plus what? 5. So we have into n plus 5 divided by n plus 5. All must be in the absolute sign, right? So we have 2n plus 5 minus 2n minus 10 divided by n plus 5, right? So we're going to have this, we'll take off this, then we have 5 minus 10 divided by n plus what? 5, right? So this is what we have. We can see that we can do some differences here. So this is equal to negative 5 absolute of that divided by what? N plus 5. Now, we can remove the absolute sign and write only the positive, right? Because we know the absolute is interested in what? The positive value, right? So, remove the absolute sign, the absolute value, all right? Then we are going to have positive 5 over n plus 5. Now, we have to find, or we want a value, all right, that is less than epsilon, as we defined over here. So what are we going to do? We are going to make sure that n stands alone, as we stated over here. All right, n must stand alone. So this implies that n plus 5 must be less than epsilon over 5. You know why? I'm trying to make n stand alone, right? So I shifted this here and then multiply here by n plus 5. So it cancels this and then it goes here. So when you do the simplification, you can have n plus 5 less than epsilon over 5. So we need n. So we say that this must go here. So we have n to be less than epsilon over 5 minus what? 5. Right. So we say that our n is less or equal to epsilon over 5 minus 5. And that is what? Our n. That is the n that we were looking for. So we can say that then for all n that is greater or equal to natural, then the big N, which is, this is any number, all right? a small number that is greater or equal to this big number, right? Then we have an minus 2 to be less than what? Epsilon. So you have been able to define this, right? Because if you have epsilon over 5 minus 5, it means that this number here is either greater or equal to this because of this definition, right? So let's go up here and do some few conclusion, then we are down the line. All right, so we come up here, then we can say that by the definition of the limit given, conclusion, we can say that by definition of convergence, of a sequence, we can say that limit as n approaches infinity, n to n plus 5 divided by n plus 5 is equal to 2. So this should be our conclusion to the problem given. All right, so that is it to this particular problem. You see, it's very, very simple, right? So just go through the process. This is a bit slight different from calculus. You know, in calculus, we always use epsilon delta. In here is epsilon to a certain number, right? That is what makes the course a bit different. All right, so give me some short break. I'll be right back with question number 1B. All right, welcome back from the short break. I believe that you have been able to go through the first problem and you are good with it. All right, now question 1B, we want to determine whether the series summation from n equals 1 to infinity into -1 to the power n minus 1 times n over n squared plus 1 converges or diverges. All right, so basically, if you have a series problem and you want to determine whether it converges or diverges, first you have to check the type of series it is. Is it alternating series or whatever, right? So in here, we can see that this series is an alternating series because of this, right? Because of that, the series is what? Alternating. So let's say that this is what we are going to do. Summation from n equals 1 to infinity, -1 to the power n minus 1, n divided by n squared plus 1, right? This particular series is an alternating series. The reason is that it contains the factor -1 to the power what? N minus 1. And that confirms that it is an alternating series, right? So, first of all, let A sub n equals n divided by n squared plus what? 1, right? So, here, the given series is alternating, right? It's alternating is alternating, right? Since it contains the factor, -1 to the power n minus what? 1. So if you see a series that contains the factor -1 to the power a certain number or a certain function, then we can say that the series is what? Alternating series. So we can apply the conditions, right? So first, remember the alternating series conditions. So we have to apply the alternating series test, right? We have to apply the alternating series test. Now, one thing that I want to chip in is that if you are dealing with introductory analysis, make sure that you write each and every step, right? Because each and every step makes sense. So you can't jump a step and move to another step, like, you understand, right? So write each and every step. If it is 2 plus 2, you write it down before you proceed toward the result. Now, the first condition is what? Positivity, or what we call the non-negativity, right? So the positivity, we know that n must be greater than what? 0, all right? And this right here, n squared plus 1 must be greater or equal to what? It must be greater than 0, right? If this is greater or equal to 0, and in the case of 0, then you have this thing to be what? Undefined. That is why we are saying that the first condition, this must be what? 0. This must be greater than what? 0. That is positivity. And then the denominator too must be what? Greater than 0. So anytime you have an alternating series and you want to apply the alternating series test, then you have to make sure that the first condition is what? Satisfied. That is what? Positivity or the non-negativity. So now we can see that this implies that an is greater than what? 0. We can see that all the conditions satisfied. So this particular thing is greater than what? 0. All right. So we can say that condition satisfied. All these steps are necessary. Condition satisfied. So the first condition has satisfied. All right. So the second condition is the monotony, right? Monotonicity, right? That word, it's very interesting word. So condition two is monotonicity, right? Or we can simply say monotony, right? So the second condition is monotonicity, right? So that is where we are going to differentiate the function, right? And see if it is decreasing or increasing. Okay, so first of all, consider the function. So we are going to consider this function to be what? F of x. So f of x should be equal to, so we change these parameters, the n, to be what? X, because we are using what? F of x. If you are using f of n, then you can use the functioning like that. But for simplicity, we know mostly we use x in differentiation and stuff. So if you see if you are going for the monotony, you have to make sure that you change the variable from n to what? X. So we're going to have x divided by x squared plus what? 1 as here. Okay, so the next thing we do is to differentiate, all right, and see if it is decreasing or increasing function. So we differentiate this, differentiate. So we're going to differentiate this particular function. And remember, I told you that in calculus, the only thing that makes work difficult is when you don't know your derivative or differentiation rules. The product, the quotient, those chain rule and implicit stuffs. So remember, if you have a function that is a rational function and want to differentiate, first you have to remember the quotient rule, and that is what goes to save us here. So we are going to differentiate this using the quotient rule. Or you can change it from this fraction to a linear function so that you use what? The product rule. But let's use the quotient rule. So we let x or u equals what? X. And then v equals what? X squared plus what? 1. Then our u prime will be 1. Our v prime will be what? 2x. Right? And the quotient rule says that if you have two functions that are dividing, then first differentiate the first function, maintain the second function, minus maintain the first function, differentiate the second function, divided by what? The square of the second function. So we are going to apply the same knowledge to teach or to chip in these stuffs. So our f prime of x will be equal to, derivative of the first function is what? 1. Then we maintain the second function, which is what? X squared plus 1 minus, we maintain the first function, which is what? X. Then we differentiate the second function to what? 2x. Divided by the square of the second function. So we have x squared plus 1 all squared. Right? So in here, we have x squared plus 1 minus 2x squared divided by x squared plus 1 all squared. So we can see that this, we reduce this one by 1. So we're going to have 1 minus x squared divided by what? X squared plus what? 1 all squared. Great. So this is what we are having. And we can do something about this, right? So the next thing we can see from this particular result is that x is greater or equal to what? 1. Right? It's either x is greater or equal to what? 1. Right? So x is greater or equal to what? 1. All right? So if x is greater than 1, we'll be having what? If x is greater than 1, we'll be having what? A decreasing function. Right? Yes, if x is still equal to 1, we'll be having what? A decreasing function, because the denominator is going to make it what? Decreasing. So we say that f prime of x is less than 0, and this implies that f prime of x is decreasing. F prime of x is decreasing. Thus an is decreasing. Thus an is what? Decreasing. And the condition is what? Satisfied. And the condition is what? Satisfied. So that is the monotony, right? The monotony condition. So you differentiate the function, then you check if it is decreasing or increasing. And right from here, we can see that if n is equal to 1, we are going to have what? 1 minus what? 1. And that is going to be what? 0 over this. And anything over 0 over anything is what? 0. So it means that f prime of x is less than what? 0. Is either equal to 0 or less than 0, because if this one too is greater than 1, then we are going to have a negative, right? We are going to have a negative. And of course, anything that we have here over this is going to what? Increases. This is going to increase it. This right here is going to increase, right? It's going to increase automatically. Whatever you do to it, it will increase because of the sign in here and the square, right? So it is a decreasing function. It is a decreasing function. So the condition 2 has satisfied. Now let's look at the third condition. Then we can conclude on this, whether it's convergence or divergence. So the third condition is the limit of terms. Condition 3, limit of terms. Limit of terms. So we are going to consider the function given or the limit given and see this limit, the series that we have been given. We are going to use the limit understanding or the limit theory to deal with this and see the result. All right. So if the result is equal to 0, then we can say that the condition is what? Satisfied. Right? So we come here, then we say that limit as n approaches infinity of the function, right? N divided by n squared plus 1, right? So you know what to do. Use from your limit theory, use this to divide each of the terms, right? So we're going to have limit as n approaches infinity, n divided by n squared over what? N plus n, this divided by what? N. And this will give us 1 divided by n plus 1 over n, right? Now we can substitute the infinite, right? So we have limit as n approaches infinity, 1 divided by n is infinity plus 1 over what? Infinity. And this is equal to n approaches infinity, 1 over infinity, right? Plus 1 over infinity is what? 0. So we have 0 here. Then we have limit as n approaches infinity of 1 over, 0 plus infinity is what? Infinity. And so we are going to have limit as n approaches infinity of 1 over infinity is what? 0, right? We know that 1 over infinity is what? Any number over a very large number is what? Will approach what? 0. So we see that this right here is 0. And you know that limit of a constant is the same constant. So we have 0 here. Therefore, we can say that condition satisfied. Condition satisfied. So by the alternating series test, we can conclude that the series converges. All right. So by the alternating series test, remember this conclusion is very, very important. So you have to make sure that you write it very nice for your tutor or for your lecturer. So given a problem, a series problem, first you have to identify whether the series is an alternating series or you have so many types of series, right? So if it's you see something of this sort, right? If the factor is -1 to the power something, right? -1. If you see something of this sort, it means it is an alternating series. Then you can apply the alternating series test. And then you go through the process that you went through, then you are satisfied. Great. So give me some short break. I'll be right back with question number 2. All right, welcome back from the short break. I believe that you have been able to go through problem number 1B and you are good with it. Now come very close and let's look at question number 2A. This is one of the easiest you can have. Now, we want to determine whether the series, this particular series, is convergent or divergent. If it is convergent, then we want to find the sum. Now, how do we know that a series is convergent? This kind of series is convergent or divergent. For this series to be convergent, then it means that when we find everything, the ratio, right, must be less than what? 1. Absolute of the ratio must be what? Less than 1. So, we are going to start the process. So we have summation from n equals 1 to infinity 3n plus 2n 6 to the power n. They are all to the power, right? Now, for our work to be very easy, first of all, split, or let me write it for you, split the terms, right? Or we say that split the series. So let's split the series. Split the series. All right. So you split the series and you're going to have this 3n plus 2 to the power n divided by 6 to the power n is the same as this 3 to the power n divided by 6 to the power n plus this 2 to the power n divided by what? 6 to the power n. So we have been able to what? Split the series. Now, the next step is to consider them one by one. So considering this one, considering this 3 to the power n, 6 to the power n, we can say that this is the same as 3 to the power n divided by 6 to the power n is the same as, you can see that they all have the same exponent, right? So we write all under in the brackets, then we use one exponent for them, right? So we can see that we can simplify the inner expression. So this is the same as 1 over 3 to the power n. So in here, we can see that our first term is going to be 1 over 3. And the ratio 2 is going to be what? 1 over 3. Right? So we're going to have, so from here, I can conclude that both this and this will be a geometric series with radius less than 1, right? So it is convergent. But let's go through the process and verify. So we take this, we know that summation from n equals 1 to infinity of 1 on 2 to the power n is the same as summation n equals 1 to infinity 1 over 2 times half to the power n minus what? 1. This expression is the same as this, right? So until you do this, you cannot find a sum. Why? Because you will not know what your A is and what your ratio is also is. So what we have done here is the same as this. Note, 1 over 2 times half to the power n to the power n minus 1. This is the same as, when it comes to indices, this is the same as this divided by half to the power 1, right? And indices says that if they have the same basis and they are dividing, you subtract the exponent. And so that's what we are having here. So this is the same as half to the power n minus 1. So we have this here. And you know that if you have this and there is a half in front, that means that you have half times half to the power n minus 1 right here. And you know that this is what? This is basically half times what? 2 over 1 to the power what? N. So this takes this, and then we have your half to the power what? N. So this here is the same as this. Okay? So we are going to use that knowledge to find the sum, because we can see that the series converges. So since the series converges, then both are geometric with series r less than what? 1. So here our A, which is the first term, is 1 over 2. Our R, which is the ratio, is also 1 over 2. So using the sum to infinity formula, we have A divided by 1 minus what? R. And then we know that A is half divided by 1 minus what? Half. And this is half divided by what? Half. Of which we have positive 1. So the first sum for this is what? Half. We are having positive 1, right? Now let's consider this as well. So when we consider summation n equals 1 to infinity 2 to the power n divided by 6 to the power n, of which this is the same as 2 over 6 to the power n. Now, we know that we can simplify that to have 1 over 3 to the power n. All right? Before we can find the sum, we have to make sure that we have the first term and then we have the ratio, right? So this is the same as half 1 over 3 into 1 over 3 to the power of n minus 1. So this expression is the same as this. So from this, we can say that our A is 1 over 3, our R is also 1 over 3. So using the sum to infinity formula, which is A over 1 minus R, we have 1 over 3 divided by 1 minus 1 over 3, and that is equal to 1 over 3 divided by what? 2 over 3. All right. right? And this, when you reciprocate it, you're going to have what? 1 over 2. All right? So the second part, we have what? 1 over 2. And the first part, we have what? 1. So the sum is 1 plus what? 1 over 2. And that is 3 on 2, which is what? 1.5. So we have the sum to be what? 1.5. So after checking whether it's convergent, and if it is convergent, we should find the sum. It's convergent because both are geometric series with radius less than 1. All of them, their radius is what? Less than 1. You can see that r is half, r is 1 over 3, of which they are less than what? 1. So they are convergent. The series is convergent, and hence we are able to find the sum. And then we had what? 1.5 or 3 on 2. So therefore, we can conclude that hence the series summation from n equals 1 to infinity 3 to the power n plus 2 to the power n divided by 6 to the power n is convergent. It's convergent. And the sum is 3 on 2, of which is what? 1.5. Very interesting problem. Very, very interesting problem. That is how you go through to find or to determine whether it is convergent or divergent. And it is convergent. This is how you find the sum. I believe it's so interesting. Give me some short time. I'll be back with question number 2b. See you right. All right. Welcome back from the short break. I believe that you have been able to go through question number 2a and you are good with it. Now, our last problem of the day is we want to determine whether the sequence Sn is equal to n over n plus 1 is bounded and monotonic, right? So when we talk about boundedness or boundedness, right, then first of all, we have to begin to think of this n, right? This n right here must be less than what? The denominator, right? And that is where the boundedness begins. So let's begin with the boundedness. All right. So solution Sn equals n divided by n plus 1, right? So we consider the boundedness first. So for boundedness, we say that since n is less than n plus 1, you can clearly see from here that n is less than n plus 1. Because if you have, let's say, n to be 1, then probably n plus 1 will be what? 2. So n is what? Less than n plus 1. Are you cool with that? Now, so we say that since n is less than n plus 1, okay, then this implies that n divided by n plus 1 is less than what? Positive 1. That makes sense, right? Because if n is less than n plus 1, then possibly we can say that the whole of this expression will be less than 1. You know why? If you have as I did here, you have n divided by n plus 1, and n happens to be 1, then we're going to have 1 over what? 1 plus 1, and this is what? 1 over what? 2. This is what? 0.5, right? And so we can say that this whole thing is less than what? 1, and it has been confirmed from here. You can pick any other number. Let's say n is equal to 2, that means that n plus 1 will be equal to what? 2 plus 1, and that is what? 3. So it means that we're going to have 3 over 3 plus 1, and that is equal to 2 over 3 plus 1, and that is equal to 2 over what? 4, which is what? Half. And it just less than 1. The numbers keep reducing. So you can see that we have 0.5 here, 0.5 here. It means that this whole expression is less than 1. Okay. So once we have understood that, then we can boldly say that n divided by n plus 1 is greater than 1. Right? As we did here, we never had n to be what? Less than 0. It's always greater than what? 0. Because if you pick here to be 1, this is going to be what? 1 plus 1, and that is 2. So 1 over what? 2 is what? 0.5. And 0.5 is what? Greater than what? 0. So we can say that thus 0 is less than Sn, and it's less than what? 1. So from these deductions, we can say that 0 is less than Sn, and it's less than what? 1. So we say that the series, hence the sequence is bounded. Hence the sequence is bounded. You see, we can see that the sequence is bounded between this and that, right? The sequence is bounded between this and that. So that is all about boundedness. That is all about boundedness. So if you have a sequence problem and you want to check for boundedness and monotony or monotonic, then first you have to look at the function, right? Try, if you don't really understand what you are doing, try numbers using counterexample, right? So if you use counterexample as I did, you see that this place, if you use n to be 1, you have 1 over what? 1 plus 1, that is what? 1 over what? 2, and that is 0.5. And 0.5 is less than what? 1. Now, come back, and you can see that n over n plus 1 is greater than 0. From our earlier deduction, we realize that we have what? 0.5, of which is less than what? 1, and it's greater than what? 0. So we can see that the boundary or the boundedness is less than 0. 0 is less than that, and is revolving within this function. So that is 0 and what? 1. So that is the boundary. All right. So hence the sequence is what? Bounded. Now let's look at the monotonic. Let's look at the monotonicity or the monotonic, right? So for monotonicity, right? First of all, we have to compute or find what we have here, Sn plus 1 minus Sn, right? We have to first find Sn plus 1 minus what? Sn, right? So you can see that we have n plus 1. So that is why we are talking about Sn plus 1 minus what? Sn. So Sn plus 1. So we're going to have compute, or what you can call find Sn plus 1 minus what? Sn. Right. So we are going to compute this and see the result, right? So we say that this is equal to, we know that Sn plus 1, we are just going to add 1 to this numerator. So we have n plus 1 divided by what? N plus 1 plus 1. So we have n plus 1 plus 1, right? Minus the Sn, so the original Sn. So that is going to be n divided by n plus 1. So we're going to have n plus 1 divided by what? N plus what? 2 minus n divided by what? N plus 1. That is very, very interesting, right? This is very interesting. When it comes to sequence, it's always interesting. It's the series that sometimes it behaves some way because we have different types of series. And don't worry about that. I'll come back to structure the course on the channel for easy understanding. Okay, so from here we can see that we have n plus 2 here, n plus 1. So we have to find a common denominator, right? So from here, our common denominator will be what? N plus 2 and what? N plus 1. So the common denominator is n plus 2 and n plus what? 1. So this goes off, and then we have n plus 1, n plus 1, minus this also goes off, and then we have n times n plus what? 2, right? So that is how the process goes. So we're going to have, we expand that, and we're going to have n squared plus n plus n plus what? 1 minus n squared minus 2n divided by n plus 2 n plus 1. Right, so this is going to give us, this will cancel this, and then we have this, and this will give us 2n plus 1 minus what? 2n. And so divided by n plus 2, n plus what? 1. This cancels this, so we're going to have 1 over what? N plus 2, n plus 1. Right? So this is what we have, right? And clearly, we can see that 1 over n plus 2 times n plus 1 is basically greater than what? 0. Right? We can see that 1 over n plus 2 times n plus 1 is basically what? Greater than 0. You know why? If you use this place to be 1 and this place to be 1, you're going to have what? 1 plus 2, and that is what? 3. And then this is going to be what? 1 plus 1, which is 2. 2 times 3 is 6. 1 over 6 is what? A positive number, all right? So it is greater than what? 0. So we can say that clearly, 1 over n plus 2 and n plus 1 is greater than what? 0. Clearly, we can say that 1 over n plus 2 times n plus 1 is greater than what? 0. And therefore, we can say that Sn is an increasing function, or it's an increasing sequence. And so we can conclude that it is monotonic. So right here, we're going to have thus Sn is increasing. Thus Sn is increasing. Thus Sn is increasing. So whatever you do to it, it will keep increasing. It will keep increasing. It will never be equal to what? 0. It will always be what? Greater than 0 because of the positive denominators that we have. Right. So that is our conclusion. We say that thus Sn is increasing. Sn is increasing. Sn is increasing. So we have been able to check for boundedness, and we have been able to check for monotony or monotonic. And that is so interesting. That will be the end for this particular lecture or this particular lesson. Thank you very much for watching. I really appreciate your time. Please, one thing you can do to help us is to subscribe. Press the subscription button, share, like, comment. Do comments. It really helps us to improve. Comment help us to improve. Thank you very much. Bye-bye.